This is the fourth video in the kinematics section. This is about simultaneous equations. Not so much a particular topic, but you might get questions which involve use of simultaneous equations to resolve. So if we're looking at the motion of a particular particle, and this is looking at in relation to the Suvat equations, constant acceleration. So we might have you know, the information on a motion of a particle gives us the displacement and the acceleration, but not the initial velocity or the time, which then obviously on that basis of that we'll be able to we won't be able to resolve it. This is all incidentally to do with the linear motion at this stage, which is what we've been dealing with in Suvat equations. So how do we proceed from there? Well, usually, well, always these kind of problems, if there are two unknowns, they will be given two sets of conditions. So we'll be given some more information, which allows us to form another equation. This looks like S equals ut plus half at squared, doesn't it? We'll be able to reformulate that, and we'll get a second equation, and we will have those same two unknowns, and therefore we can resolve because two equations in two unknown simultaneous equations. So that's the basic idea. So, and the sort of conditions that allow us to formulate these equations, but basically we sometimes call those boundary conditions. Worth noting that we may also see simultaneous equations arising in vector problems. We'll be doing this in a later video. That's where we've got motion in two directions, maybe east and north, X and Y, or whatever we choose to call those directions. So they can arise from that. They arise in forces as well in mechanics, because we do have two, we're looking at forces in two different directions. So if that does make sense, you can have a look at the forces section. But in actual fact, simultaneous equations is something that characterizes all of A-level, really. Just if you think back to your GCSE, you perhaps note that there were questions where you had to formulate an equation from some problem statement, and it was the formulation of that problem, then solving that equation that gave you, as a sort of thing that would give you the sort of marks that you might need for grade 7, grade 8, or grade 9. In A-level, what characterizes A-level, the sort of corresponding thing, is the ability to be able to formulate simultaneous equations. And that kind of goes right through not only kinematics, but also mechanics in general, and really through all of pure and applied. So you'll see that sort of thing cropping up all the way through. This is one example. Okay, so the best thing to do is proceed to an example. This is kind of quite a nice example that illustrates that. A train which is moving with uniform acceleration is seen to travel 800 meters in 1 minute and 1200 meters in the next. Find the speed of the train, the beginning of the first minute, the initial velocity, and the acceleration of the train, and then we go on to find the speed of the train at the end of the second minute. So if we look at the first minute alone at the moment, and we just chart out what we know. So the distance is 800, the time is 60. The initial velocity, I've kind of used both u and v0 here. We don't know the acceleration either. So when we use our displacement equation and substitute in the values that we've got, we're still left with u and a here in this first equation. Okay, so what do we do? Well, if we now have a look at this first 2 minutes, now there's different ways of doing this, but easiest way, I think, is to sort of aggregate these two. So we're looking at 2 minutes travel, so that's 2,000 meters, 120 seconds. That's equals 2,000 seconds, 120. We still don't know the initial velocity. We still don't know the acceleration. But when we plug those into the displacement equation, we get this, and we can see that this and this, two equations in the same two unknowns, and we can resolve these using the methods that we use for solving simultaneous equations. So without just going through that, I assume that you'll know how to do that. We can just work through and find out what A and U are, and that's going to give us a U of 10 meters per second, and an acceleration of 1/9 meter per second per second. So that's basically answered A and for parts 1 and parts 2. And then it says the speed of the train at the end of the second minute. We're talking about speed here because we know the direction, and it's there's only one direction, and it's always going to be positive. So speed and velocity, kind of the same thing here. So after 2 minutes, we're just plugging these things into one of the Subat equations. So we know the total displacement is 2,000. We know the time 120. We know the initial velocity is 10. We don't know the final velocity. That's what we're trying to find out. We know the acceleration. So we got a choice of what we use here, but probably the velocity equation, V equals U plus AT, is probably the one to use here. And if we plug in the U that we know from here, the acceleration that we know here, and the time that we know from here, plug all those in, we get the final velocity is 23.3 recurring meters per second, which I've written as 23.33 meters per second to 2 decimal places. Always put your accuracy in. Okay, so that's a fairly straightforward example, I think, but it's something to watch out for. These questions do crop up from time to time, and but in reality, if you're dealing with simple sort of linear motion, constant acceleration, they shouldn't be too challenging for you if you can understand that. Okay, so that's it on that topic, and we've got more kinematics to do, and I'll see you in the next video.